Take two identical glasses. Fill one with hot water straight off the boil. Fill the other with cold water from the tap. Put them both in the same freezer side by side at the same moment. Which one freezes first? You already know the answer. Everyone knows the answer. The cold one wins. It has a head start, it is closer to the finish line. Asking the question at all feels almost insulting. So hold that certainty for a second, because in 1963, in a school in Tanzania, a teenager watched the hot one win. His name was Mpemba, and when he asked his physics teacher how that was possible, he did not get an explanation. He got humiliated. The teacher told him in front of the class, "You were confused. That cannot happen." It became a running joke at the school. Whenever a student made a mistake, the others would laugh and call it Mpemba's physics. Here's the problem with that joke. 6 years later, Mpemba's name was on a published physics paper describing exactly what he saw. And more than 60 years later, his name is attached to one of the strangest, most stubborn arguments in modern science. Not an argument in classrooms. An argument in laboratories, in the pages of major journals between physicists using precision probes, laser traps, and single floating atoms, over a question you could test tonight with two glasses and a freezer. Does hot water really freeze faster than cold? And I want to be honest with you right from the start, because that honesty is the whole point of this video. This is not one of those stories where I hold back a clean answer to keep you watching. There is no clean answer. Some physicists say the effect is real. Some say 60 years of results are one long measurement error. And the strangest group of all says the effect is real. Just not really about water. Everything in this video comes from published research, and wherever the experts disagree, I will tell you exactly where and why. Let's go back to where it started, because the origin is not a laboratory. It is a cookery lesson. Mpemba Secondary School, Tanzania, 1963. The students are making ice cream. The recipe is simple. Boil milk, stir in sugar, let the mixture cool to room temperature, then put it in the freezer. But freezer space is limited, and there is exactly one slot left. Mpemba does the maths every student has done at least once. Waiting is losing, and he puts his mixture in boiling hot. An hour and a half later, his mixture is frozen ice cream. His classmates' cooler mixtures are still thick liquid slurry. Now, most of us would shrug at that and move on. Mpemba did not. He carried the question with him for years. And when a visiting university physicist named Dennis Osborne came to give a lecture at his high school, Mpemba raised his hand and asked it straight. If you take two identical containers with equal volumes of water, one at 35 degrees and one at 100 degrees, and put them into a freezer, the one that started at 100 degrees freezes first. Why? The room laughed. Osborne did not. He gave what might be the most important answer a scientist can give. He said he did not know, but he would try the experiment, and here's the part the laughing students never saw coming. Osborne went back to his lab, ran the tests, and saw the effect. In 1969, the journal Physics Education published a paper on it with two names at the top: a university physicist and a secondary school student. The phenomenon has been called the Mpemba effect ever since. But there is a twist buried in the history books, and it makes the mystery much older. Aristotle described hot water freezing faster more than 2,000 years ago. Francis Bacon mentioned it, so did Descartes. Which means some of the sharpest minds in history noticed this thing, wrote it down, and then science essentially filed it under folklore for centuries. Here is the argument against the Mpemba effect, and I want you to feel its full weight because it looks completely airtight. Picture cooling as a road. At one end of the road is boiling hot. At the other end is 0, the freezing point. Cold water starts partway down that road, say at 25 degrees. Hot water starts near the very beginning at 90. Now here is the trap. For hot water to freeze, it has to cool down. And on its way down, at some point, it must pass through 25 degrees. The moment it reaches 25, it should be identical to the water that started there. Same temperature, same water, same freezer. From that point on, the race should be a perfect tie, except the hot water has already wasted all the time it took to get there. In other words, the hot water's journey contains the cold water's entire journey plus extra. It is like two runners on the same road, where one starts 5 kilometers further back. The runner behind cannot win. Not without cheating. Not unless, and remember this phrase, because the entire mystery turns on it, not unless they are not actually running on the same road. That is the paradox. Any explanation of the Mpemba effect has to find a different road. Something about being hot has to leave a mark on the water, a kind of memory that survives even after the temperature has fallen. Otherwise, the overtaking is flatly impossible. And before we meet the suspects, there is one more complication, and honestly, it explains half of the 60-year fight on its own. And different experiments over the decades measured different ones, then argued as if they had measured the same thing. Keep both of those ideas in your pocket. Over 60 years, physicists have assembled a lineup of mechanisms that could, in principle, let hot water take a different road. Here are the 5 that matter. Suspect 1, evaporation. Hot water steams. Every wisp of steam is mass leaving the glass, and it leaves carrying a huge amount of heat with it. So by the time the hot sample cools down, it is no longer the same race. It is a lighter runner. Less water simply takes less time to freeze. Experiments in sealed containers where evaporation cannot remove anything have still sometimes reported the effect. So evaporation can be a contributor, but it struggles to be the whole story. Suspect 2, convection. Water does not cool evenly like a metal block. It stirs itself. As the outside cools, currents form, and in initially hot water, those currents are much more vigorous. They keep delivering warm water to the surface, where heat escapes fastest. This creates something wonderful called a hot top. And here is the key. Those violent currents do not vanish the instant the average temperature drops. The formerly hot water can keep its aggressive circulation and keep dumping heat faster, even when a thermometer says the two samples now match. Notice what that is. That is a memory of having been hot. That is a different road. Suspect 3, dissolved gases. Cold tap water is full of dissolved air. Heating water drives that air out, which is why you see little bubbles form on the side of a pan long before boiling. Water with less dissolved gas is not quite the same liquid. Its ability to move heat around and to form ice crystals may differ. Some researchers think degassed water freezes more readily. Others are unconvinced. This suspect has never been cleared and never been convicted. Suspect 4, and this one is my favorite, supercooling. Here's something most people never learn. Water does not automatically freeze at 0 degrees. Clean, still water can drop to -5, -8, sometimes far lower, and stay stubbornly liquid. It is waiting for a trigger. A speck of dust, a scratch on the glass, anything that gives ice crystals a place to start. That trigger event is called nucleation, and it is partly a dice roll. Now the twist. Some experiments found that formerly hot water tends to supercool less. It gives up and freezes at a warmer temperature sooner, which means the hot water might not be cooling faster at all. And suspect 5, the embarrassing one, frost contact. Put a hot container on a frosty freezer shelf, and it melts the frost beneath it. then refreezes into direct icy contact with the metal. The cold container just sits on top of the frost, insulated by it, like a jacket it never asked for. The hot container has accidentally plugged itself into the freezer's cooling system. It is mundane, it is unglamorous, and in a real kitchen it might genuinely decide the race. So which suspect did it? Here's the frustrating, honest answer. Each one of them explains some experiments. None of them explains all of the experiments, and the effect itself behaves like a ghost. In 2016, two researchers at Imperial College London, Henry Burridge and Paul Linden, decided to end the argument, not with a new theory. With brutally careful measurement, they ran cooling experiments designed to strip away every excuse. Identical samples, controlled conditions, precise temperature probes, and one clear question. Does initially hot water reach 0 degrees faster than initially cold water? Their answer, published in scientific reports, was blunt. No, never. In their words, no matter what they did, they could not observe anything like the Mpemba effect. But the truly devastating part of their paper was not the absence. It was the autopsy. They asked how so many earlier experiments could have seen the effect, and they found a suspect inside the thermometer itself. Water cooling in a container is not one temperature. The top, the middle, the bottom, and the edges can all differ at the same moment. Burridge and Linden showed that moving a temperature probe by about 1 centimeter, one single centimeter of placement inside the container, could produce apparent differences as large as the entire Mpemba effect. 60 years of mystery, possibly resting on where someone happened to poke a thermometer. Case closed? Not quite. Because the counterattack came fast and it was fair. Critics, including the chemist Nikola Bregovich, pointed out that Burridge and Linden had measured the time to reach 0 degrees. But water reaching 0 is not water freezing. Remember supercooling. Freezing begins with nucleation, that dice roll moment when ice finally takes hold, and their experiment deliberately stopped short of it. In other words, said the critics, you carefully measured the wrong finish line, so even the debunking is contested. And this is the honest state of the water question today. One camp says the effect in plain water has never survived a rigorous test, and the historical results are artifacts of sloppy measurement. Another camp says the effect is real but conditional, appearing only when specific mechanisms line up, and the experiments keep coming. Recently, one research team reported that when they filled a freezer environment with ice nucleating particles, the trigger dust that supercooled water is waiting for, hot samples, froze faster than cold ones repeatably, especially when the starting temperature gap was large. That result is new and still being digested by the field, but it points in the same direction as the supercooling story. In 2017, two theoretical physicists, Zhiyue Liu and Oren Raz, asked a question that changed the field. Forget water. Water is a nightmare. Too many variables, too much dirt, too much chemistry. Is there any physical system, even an abstract one, where starting hotter genuinely lets you finish cooling first? Their answer was yes, and the reason is beautiful. Here's the idea. We describe a glass of water with one number, its temperature. But that number is a summary, an average, a headline. The true state of the system is millions of details. Where the energy sits, how the molecules are arranged, which configurations are occupied. Cooling is not a ball rolling down a single track from hot to cold. It is a journey across a vast landscape of possible states, and that landscape has valleys, ridges, slow paths, and fast lanes. Now here is the trick. Heating a system does not just raise its headline number, it rearranges all the fine details. And that means a hot system can begin its journey from a completely different location on the landscape, a location that happens to sit right next to a fast lane. The cold system, despite being closer as the thermometer measures things, can be stuck starting beside a slow, boggy path. The two runners were never on the same road. That intuition you had at the start of this video, that the hot sample must retrace the cold sample's exact journey, is simply false for systems like this. It is only true if the system has no memory. And real systems, it turns out, remember, that was theory. Then in 2020, it became fact. At Simon Fraser University, Avinash Kumar and John Betchhofer built the cleanest possible version of the race, not water. A single microscopic glass bead held in a precisely shaped energy landscape by lasers, cooled thousands of times from different starting temperatures. The result was undeniable. The hotter starting bead reached its cold, settled state faster, reliably, repeatably, on demand. They even found what theorists call the strong Mpemba effect, special starting temperatures from which the relaxation is exponentially faster, the physics equivalent of finding a wormhole through the landscape. And once physicists knew what they were looking for, they started finding it everywhere, in granular materials, in polymers, in ice-like crystal structures called clathrate hydrates, in magnetic materials, even in light, and then, in 2024, in the most extreme place imaginable. 3 separate laboratories reported Mpemba-style effects in single-trapped ions. An effect first noticed in a batch of school ice cream is now a measured phenomenon in quantum mechanics. So the modern picture flips the whole question. The Mpemba effect, as a family of effects, is real. So let's give the verdict honestly in 3 lines. Does hot water freeze faster than cold in your freezer? Sometimes, under some conditions, and physicists still argue about whether that is deep physics or leaky experiments. Anyone who tells you the answer is a simple yes or a simple no is skipping the best part. Is the Mpemba effect real? Yes. As a wider family of phenomena in beads, crystals, gases, and atoms, it is measured, replicated, and understood well enough to engineer. Systems can remember where they started, and that memory can beat a head start. Was the teacher right? No. And that is the line I want you to take with you. The teacher said that cannot happen. And he said it to a boy holding evidence. Erasto Mpemba went on to a career in wildlife management, not physics. But his teenage question outlived the century it was asked in. And his name is now attached to effects in quantum systems his teacher could never have imagined. So tonight, if you like, run the 2 glasses yourself. Whatever result you get, you will be looking at something remarkable. Not a settled fact and not a myth. A live, open argument in physics, sitting quietly in your freezer, started by a student who refused to be laughed out of a question.